Loud. Okay, so we have classes on Wednesday, 2 hours, and 1 hour on Thursday from 1:40 to 2:30. So basically today, the first 2 hours, we will go over the syllabus first. So I'm sharing the syllabus. I hope that all of you can see it. And then after the syllabus, we will slowly start our subject matter and regarding aerodynamics 2 course content. And we will watch 2 short videos about, or let's say related to the course content as a brief introduction. So let's start with the syllabus. By the way, if you have questions, you can interrupt and ask anytime, or you can type it up in the chat box. I can try to answer. So yes, this is Aerodynamics 2, 342, and it's a 4-credit course. And the course catalog description is here. I'm not going to read it. You can read it yourselves, but I will go over the course material in much more detail right now, pretty soon. You know me, my office is in the 3rd floor of Rüzgar building. And we have listed 3 course assistants, but in reality, we will have 4 course assistants. Which actually we got to know today. There's going to be 1 more. So Battal, Burhan, Hassan, and Ali Ata will be our course assistants for this course. And I'm going to skip the course of learning outcomes and program matrix. So regarding instructional methods, as we have done similarly for the 341 course, the Aerodynamics 1 course, we will have online lectures every week using Zoom, and the link is available on OttiClass. And we record, as you know, all lectures. You can, and it's saved automatically on OttiClass. So you can later watch them, or you can download them. Of course, when you download them, as you know that it's for your own use, you can listen up in your own computer and everything. You are not allowed to share it on any platform. So it's for your own use. Because as course instructors, me and Mustafa Hoca has the copyrights. So therefore, we will conduct classes through Zoom, and of course, I strongly encourage you to ask any questions or have discussions during the class. So, tentative weekly outline. So this is basically the core of the class regarding the subject. So we will discuss more about it later, but aerodynamics 2 is quite different than aerodynamics 1 in terms of subjects, but in terms of flying vehicle applications, we need to learn everything that is included here. And it's basically divided in 2 parts. This course is divided in 2 parts. The first part is what we call implicit compressible flow. So it's basically, I can say, related to high-speed aerodynamics, I can say, okay? This high-speed can be subsonic or supersonic or hypersonic. We will see all of these. So we need to understand as aerospace engineers the flow physics and related mathematics as applied to high-speed flying vehicles. Okay, this could very well be a passenger aircraft. This could very well be a fighter aircraft, manned or unmanned, or this could very well be a missile, a rocket, for different applications. So basically, until let's say until the end of week 8, as you can see here, let me scroll up a little bit. Basically, we will cover all subjects related to these high-speed flying vehicles. So it's under the subject of inviscid compressible flow, and it requires a solid knowledge of fluid mechanics, solid knowledge of thermodynamics, and some heat transfer. Okay, so this is, let's say, complementary to the topics that you learned in aerodynamics 1, which was basically mostly inviscid incompressible flow. Now we are dealing with inviscid compressible flow. So we will see what what we mean by compressibility and all that. The second half of the, or second part of the semester, starting from week 9 until the end of the semester, is basically incompressible but now viscous flows. Okay, so in aerodynamics 1 we were dealing with incompressible inviscid flow. So everything that we learned in 341 regarding like potential flow theory and all that, you know, all the mathematical methodologies that we learned were related to incompressible inviscid flows. But now we will learn incompressible viscous flows. So basically, we will expand the concept that you learned probably in the heat transfer class, the concept of boundary layers. So boundary layer types, how to analyze them mathematically, and why do we need to consider viscous effects and all that will be covered from starting from week 9 until the end of the semester. And all the related chapters in your textbook, Anderson's aerodynamics book, is listed here. So I strongly suggest, first of all, you go to the syllabus syllabus web page for this class, you know, in order to see the relevant reading. And I strongly suggest you to read these throughout the semester. The course textbook, as you know, is Anderson's Fundamentals of Aerodynamics book. And as a supplementary reading, just let's say, if you would like to get additional information on the topics that we're going to cover, you can basically use Bertin's Aerodynamics for Engineers book as well, but that is not our main textbook. Our main textbook is Anderson's Fundamental of Aerodynamics. Now, regarding assessment of your learning. So in this class, we will have 4 assignments. And as usual, we will have laboratory assignments. Normally, I will talk about the details. 1 online midterm exam and a final exam. Final exam is going to be in July. So I don't know the situation in July, if it's going to be whether online or face-to-face, we will see altogether. But let's start with the assignments. These assignments will be 4 assignments. These are not like these will be not like homeworks. These will be more like 4 small projects. So regarding the workload of this class, I will talk about it in a second. Let me first talk about the laboratory assignments. Normally in this class, we have 5 experiments. So experiments will be conducted similar to what we have done in 341. So there will be videos and you will get data, you will submit reports, and course laboratory assignments could be more than 5 this semester, but we will see. And midterm exam will be online. So as usual, you will have assistants will coordinate this, cameras on, microphones on, and questions will be revealed. And you will have to finish up your solution, scan your or take a photograph of your solution, upload it, and that's how we're going to conduct the midterm exam, which is going to be on Tuesday, May 4th, 2021. Okay, so mark it up, please. It's also, it will be marked up, or soon, maybe it's already marked up on department's calendar website, department's website, the calendar on department's website. Now, regarding all this course workload for you guys, from last semester, we have went over all the feedback that we got from you from student evaluations. We have read all your comments in detail, and we have discussed them among us, and thank you for providing these, first of all, feedback. And especially regarding the workload, we understand your concerns. So basically, based on your concerns, especially regarding the unbalanced distribution of workload throughout the semester, that's a fair criticism. We accept that, and we will try to manage that better this semester, of course, coordinating with the course assistants, especially regarding the dates of assignment dates for these little 4 projects and everything. Of course, distribution of the laboratory workload. We will try to distribute this better throughout the semester. Our semester goes until end of June. So we will try to have a better distribution compared to the course conduct that we did last semester. So this is how we're going to assess, try to assess how well you actually learned in this class. Regarding these assignments, midterm, laboratory, midterm, and final, the course grading assignments will be 20 grade points. Laboratory assignments will be again 20 grade points. Midterm exam will be 25 grade points, and final exam will be 35 grade points. That's how we're going to have the grading distributed among these assessment tools. Now, coming to course policies. First of all, of course, let's start. Attendance is not mandatory to online classes, but we strongly advise them. You can, of course, always download the course later, listen to it later. You can do that, but attending the class, listening to other students' questions, maybe asking questions yourselves, getting answers and interaction is very important. So we strongly suggest that you follow the lectures regularly, because our lectures, as you know, will be synchronized classes every week. Late submissions of any assignments, I mean the short project assignments, lab reports, or during your midterm and final exams will not be accepted. Okay, so this is we suffered a lot last semester because many students are exploiting this and not managing their time accordingly. Managing your time, providing a solution, and submitting it in the given submission period is a part of the exam. If you cannot manage your time, you will not be graded. So we will not accept any kind of late submissions this semester. Okay? So get yourselves ready. Makeup exams. Of course, there will be no makeup exams for assignments or laboratory, but there will be one makeup exam at the end of the semester for those of you who has a valid excuse, probably, and valid excuse meaning a medical condition supported by a doctor's report, or maybe a family condition. Of course, those are perfectly fine. There are acceptable excuses, but anything else, other than those, most probably we will not. We will of course assess your excuses, but only these conditions will be basically acceptable. So if you provide a doctor's report and everything, you will be eligible for a makeup exam. Final exam entrance condition. In order to take the final exam, you will have to take, first of all, you will have to take the midterm exam, and you will have to collect at least 25 points out of 100 to get the to be eligible to get into the final exam or to take the final exam. Okay, and as I've said, laboratory documents and data will be provided, and you will. That's how we are going to conduct the laboratory. But one thing that I must add here is that this semester there will be no oral exams. Okay, because we tried to, since we are going through a pandemic and now it was a transition period between face-to-face and online, we wanted to give a chance for you to, you know, basically a second chance for those who wanted. It was voluntary, if you remember, but we did not get good feedbacks from you. So we are not going to do any additional oral exam. You will just take these, you will submit your assignments, you will submit your lab reports, take the midterm and final exam. If you have a valid excuse, you will get a makeup exam. That's it. You will get your grade based on those. Now, of course, other. Now, in the evaluation of exam papers, 20% of the question will be deducted for unorganized and messy answers. Okay, because we are grading, and this is a crowded group. Aerodynamics 2 class is a crowded group, and we are doing online examinations. And you submit your digital file, whether it's a PDF or a JPEG, whatever, you submit it, and we grade your papers based on that. And sometimes due to this digital low quality, we are already suffering a lot. And if your paper is, in addition to that, already very much messy and unorganized, it makes very difficult to even read your writing. Okay, so aside from the technical difficulties that may be related to scanning and everything, we expect you to prepare an organized and nice and neat solution paper. Okay, so this is another addition to our policy. Our objection periods, you have, of course, a right to object to your grading. That's fine. Any grading, assignment, lab report, midterm or final, or your makeup. It's 1 week after these are announced. The grades are announced. Okay, you can basically object, and we will consider that. As we have been doing for some time, we will apply catalog grading rules. Okay, so like we did last semester. From your feedback that we got from the evaluations, some of you were not happy about it. Well, the overall, I mean, and let me give you another information. The overall average of aerodynamics 1 class was close to 70. Okay, it was 60 something. So catalog grading was not that bad. I mean, if the average turned out to be, I don't know, 30, 35, I would understand that, but the average was quite reasonably high, I must say. Okay. So some of you said, oh, we immediately lost interest as soon as we heard it's catalog grading and everything. Well, you have to deal with this. Catalog grading will be applied. So you have to, of course, we have that in mind when we are preparing questions and everything for the exams and assignments. So you will have to adjust yourselves also. Okay. We have finally in the syllabus page, you can read yourself information for students with disabilities. You can, if you're a student with a disability, we will basically apply the university policies regarding that. And academic honesty is the statement, but honesty in general is not a statement. It's a life philosophy. So we expect that you adhere, you basically grasp, and you obey academic honesty, or in general, you have to be an honest person in your lives. And as an engineer, you have to do that because your entire life is not this school, right? Someday you're going to graduate, you're going to go into real life, and you're going to deal with real life problems. If you're not honest, you will suffer when you face with real life problems as an engineer or in your personal lives. So just as your older professor, I strongly suggest for you to follow this behavior. So basically, this is how we're going to conduct this class. If you have questions regarding the course conduct, we can discuss it now. Then I can go over, I can follow up, I can start talking about the class material. Let me open up the chat box. I think, so Thailand is asking, could we able to use the lab grades that obtained in previous years? I think that we have a policy regarding that. We can maybe add it to the syllabus. I think you can. You must have had a minimum grade in the previous years. I think I will let the assistants know to add it to the course syllabus page. Okay, Thailand.
Hocam,
Evet.
Could you give us a hint about what will be this assignment would be like?
I mean, they are not going to be like simple homework problems. Maybe they will require maybe some coding, like little projects, I must say. Small projects. Mm-hmm. Because normally we have 14 weeks. I know that in some of your classes, for 14-week semester, you get probably 10 plus homeworks, but those 10 plus homeworks maybe, and we only have 4 assignments, but the content will be a little bit more involved than that, I must say. Melih, I think Melih, it was you asked the question.
Yeah, it was me, hocam.
Mm-hmm. Any other questions? Onur asks, who did not want oral exams? Of course, I cannot say that, okay? But this semester, there will be no oral exams. Any other question?
Actually, about that, I think, and some of my friends also think that oral exam helps us in the course. I mean, I also took the oral exam, and it helped my grade. And also, I think I was able to express myself better than written exam.
Mm-hmm. Anyway, this is currently our decision, but anyway, we will see how the semester goes, okay?
I understand, hocam. Thank you.
Mm-hmm. Any other questions?
I have a question. Will we use MATLAB for the assignment code?
I mean, if it's a coding, if the assignment requires some kind of coding, MATLAB is one option. If you know MATLAB, you can use MATLAB. Or if you know Python, you can use Python. If you know Fortran, you can use Fortran. It's your choice.
Okay, thank you.
Mm-hmm. These will be, Thailand is asking, are these going to be individual assignments? Yes, they will be individual assignments. Okay. Any other questions?
Hocam,
Mm-hmm.
about laboratory materials, should we contact with assistants or
about what?
Last year semester, some laboratory videos were not understandable in the terms of teaching.
Mm-hmm.
Regarding this topic, should we contact with assistants or?
this semester for aerodynamics 2, or all of our laboratory videos are already ready. Last semester they were not ready and we had to shoot them, and there was some timing issues related to that, and you suffered because of that, we understand. But this semester they are already ready, and I think they are good quality this semester. But anyway, if you cannot understand something, you can contact us, or I mean, it would be better first to contact the assistants, course assistants. But you can also, for example, if you're sending an email, just CC me and Mustafa Hoca regarding that. Tamam. Melih, was it you again?
Yes, thank you, hocam.
Okay. Let me stop sharing. So please go to course syllabus and read this. I mean, it's going to be there anyway. Anytime you would like, you can read it. So let me stop sharing this, and first, let's see, where should we start? What should I share first? Just a second. Share the whiteboard. So I will first talk a little bit about some general subjects, and we will talk about the and we will watch 2 short videos. Can you see my whiteboard? Can all of you see my whiteboard?
Yes,
okay,
we can.
Good. So as I said, I was talking to you guys about the syllabus and course subject matter. The first part of the semester until the end of 8th week, our topic is, as I said, inviscid compressible flow. Okay, we will see a lot of details about inviscid compressible flow. Okay. First of all, why are we, as I was telling you, why are we interested in inviscid compressible flow? Is the fact that we are interested in high-speed aerodynamics. That's why, and in high speed, when the flow around a vehicle, around an aircraft is, let's say, fast enough. So you can say, okay, what do you mean fast enough? So you know that we categorize this speed based on flight Mach number. So we will talk about definition of Mach number and everything. But generally, when you fly fast enough, start flying fast enough, and meaning that your Mach numbers flight Mach numbers are becoming higher than a certain value, the flow happening around your flying object is not incompressible anymore, meaning the density of the fluid actually starts to change. Well, this effect has big impact on flow physics, has big impact on load calculations on your wings, lift drag calculations. So we really need to understand then what is the flow physics when I start flying fast enough. So generally, as I said, for let's say designating flow speeds, we that we use the technical term Mach number. Mach is the last name for Ernst Mach, Austrian physicist. And we use the symbol M for this, and we categorize our flying regimes, I must say, based on this Mach number. So we partly have seen this in last semester's classes. So first, of course, when we say Mach number is less than 1, by the way, Mach number is basically related, or maybe I should write the equation here. Let me erase this. The equation is that it's the ratio of your flight speed to the speed of sound. Okay, so A is speed of sound, and this changes with temperature, and temperature changes with altitude. So your flight altitude, so this means that speed of sound changes with your altitude, and this is your flight speed. Okay, so if this number is equal to 1, we say Mach number is equal to 1, we say we have the sonic condition. So maybe first I should write that in categorization. So when I say Mach number is equal to 1, then this means you are flying at sonic condition because your flight speed is equal to the speed of sound at that altitude. This is known as the sonic condition. Well, if you are flying slower than the speed of sound at that altitude, we say that this is subsonic flight. Okay, subsonic flight. If it is greater than 1, so you're flying faster than the speed of sound, we say that this is supersonic flight. Okay, or we also base our flight vehicles, we categorize flight vehicles, aircraft based on their design Mach number, flight Mach number. So we say this is a subsonic aircraft. We say this is a supersonic fighter aircraft. So it's basically related to this. Also, when Mach number is greater than 5, we have a special name for it. We say this is hypersonic. Okay. Now, coming back to subsonic, we actually divide this also into 2 regimes. If Mach number is less than approximately, I must say, about 0.3, okay, we say that this is incompressible flow regime, incompressible flow. Okay, so we have dealt with incompressible inviscid flow last semester most of the time. But if you start flying fast enough, so if Mach number is subsonic, but now greater than 0.3, now we start to see compressibility effects. So we have compressible flow. And of course, obviously, if you're flying supersonic or hypersonic, it's all compressible flow after 0.3. Okay. So there's a very special flight regime, which brings in very much difficulties in high-speed flight. So we also have a special name for this. If you are flying somewhere between 0.8 Mach number and 1.2, this is a very special flow regime with additional difficulties and additional flow physics that's going on. We call it transonic flow regime because it's basically a transition between subsonic and supersonic. So we give a special name for it. We call it transonic. Okay. So basically, our aerodynamics approach into, or categorization of aerodynamics, I must say, is based on this Mach number, and also therefore categorization of flight vehicles are based on this Mach number or Mach number based categorization. So if somebody is talking about a subsonic, for example, cargo aircraft, you must ask whether it's low subsonic or high subsonic, for example. You must ask that question to understand whether it's flying in an incompressible regime or flying in a compressible regime. If somebody's talking about a hypersonic flight, a hypersonic missile, for example, you must understand that that is probably flying faster than Mach 5 and everything. So so this is Mach number based categorization. Just before we finish the first hour, I would like to introduce you another categorization related to aerodynamics in general. In general, we divide aerodynamics into two, and in the undergraduate level, we teach you only one of them. The first one is the one that we have been teaching you since the start of the fluid mechanics classes. It's called continuum flow. Continuum flow, okay? So we teach you the definition of continuum in the very first days of fluid mechanics. And we teach you the definition of Knudsen number and everything. If you do not remember these, please revise your fluid mechanics notes. So we deal with continuum flow, and continuum flow means, you know, the air that we are dealing with, air or any fluid in that matter. The molecules are, or the mean free path between molecules are small enough so that I can assess the fluid as a continuum, meaning that instead of dealing with the fluid, whether it's air or other gas, it's dealing with the fluid like it's composed of individual molecules. Well, in reality, of course, they are composed of individual molecules separated by a certain distance. But if they are close enough, we say that, okay, we can apply continuum hypothesis, and we can, for example, define what we call a fluid element. But if these molecules, so we don't, for example, when we write momentum equation, momentum conservation equation, for example, we do not write it for each and every single molecule. We say, we define a region in space. We say this is a fluid element. And then we develop all of our equations, you know, conservation equations, continuity, momentum, energy, based on that fluid element. That's called the continuum approach. But now, since we are going to be, I mean, once we deal with, for example, high altitude flights, okay, for example, re-entry from space to Earth's atmosphere or any planet's atmosphere, the gas, the air, or if it's other planet, it could be other gas, the molecules may not be very close to each other. They may be very much separated, okay? So that's called rarefied flow, okay? Which means that we are dealing with very low density and basically free molecule flows. So in that case, we cannot apply our continuum approach to that kind of flow. This rarefied flow is out of the scope of our undergraduate education. This is an advanced topic. If you're interested, that you can find graduate level classes. But we are dealing mostly with the left-hand side, the continuum flow, and we generally divide it into two parts as well: viscous flow and inviscid flow. Okay, and both of them, both viscous and inviscid flows, and we will see effects of viscosity this semester in great detail, can be incompressible or they can be compressible. Okay, so inviscid incompressible flow, here that was our 341 class. Inviscid compressible flow is 342 class. Viscous incompressible flow is also 342 class. Viscous compressible flow is also an advanced topic and not in our undergraduate curriculum. So we teach you the fundamental basics of all of these, and all these flows here that are listed under continuum assumption: viscous incompressible, viscous compressible, and the related inviscid flows. All of these can be subsonic, can be transonic, can be supersonic, or can be hypersonic. Okay, so we will see great details about these. Now, one additional, let's say, introductory information before I finish up this hour is this. As you might have seen since last semester, the topics that we mainly cover when we are doing aerodynamics teaching or aerodynamic analysis is very much heavily based on fluid mechanics concepts, right? Control volume analysis, the conservation equations, differential analysis, very much based on fluid mechanics. But now, in addition, once we start dealing with high-speed flows and once we start dealing with these high Mach number flows where density is changing, the fluid mechanics by itself is not enough to do everything that we would like to do. So in addition to all of these, now we will cover a lot of basics now based on fundamental thermodynamics as well. Okay, so aerodynamics 342, especially the compressible flow part, is heavily based on fluid mechanics plus thermodynamics, and we will revise the thermodynamics concepts, like first law of thermodynamics, which is conservation of energy, first law, and second law of thermodynamics, which is basically the entropy and loss generation. We will investigate, we will learn other concepts like what is a perfect gas. Actually, that's going to be the first concept that we're going to learn. What is internal energy, what is enthalpy, and how do the energy transformations happen? How do we make use of, how do we actually couple thermodynamics equations with fluid mechanics equations to come up with energy conservation? So how do we, for example, calculate if an aircraft is flying at, let's say, a supersonic speed, if it and it generates what you call shock waves around it? What is a shock wave? How do we handle the flow that is passing through a shock wave? We will have to combine basic fluid mechanics and basic aerodynamics equations with thermodynamics equations, okay, to basically satisfy energy conservation especially, okay? So this is kind of, let's say, a very broad introduction to what we're going to cover in this class. After our break in the second hour, since I showed you this categorization based on Mach number, we will see two videos. One of them actually shows you this, gives you some information related to these high-speed flights, and the other actually gives you a nice comparison of, since we are aerospace engineers and we are designing basic aircraft, a nice comparison video of the fastest aircraft in the world that humankind have designed since the first flight happened in 1905. Okay, so it's 2:29 right now. I will pause the recording and let's give about a 10-minute break, and I will be back at 2:40. So let me first stop sharing this and pause recording. Okay, so let me first share my screen. First, this video. Sorry, I have to do it right. Share sound. Okay, this one. Okay, now before I start the video, I forgot to make another announcement. Most probably, I mean, you know that we have lots of stuff to cover, and generally we do not have time to solve sample problems and all that, but most probably we will have recitation hours this semester. The hour times will be announced, and the course assistants will solve sample problems regarding the course material, the subjects that we have discussed. Okay, so that's, I forgot to make that announcement in the previous hour. So now let's start with this first video. Can you all see the video?
Yes, yes.
At least can one of you see the video?
Yes, sir. Yeah.
Okay, I think I did not hear if you had answered my question because my speakers were muted. I guess you can see, right?
Yes, we can. Hocam.
Okay, thank you. The first one is, I mean, we last hour we talked about these, high-speed aerodynamics. So when we talk about high-speed aerodynamics, so we are talking about fast-flying aircraft. So I just wanted to show you this video. This is the 10 fastest aircraft ever recorded. So let me start, and let's see.
In the past, people only dreamed about flying. The things have changed now when we discovered the basics of flying. Here are the top 10 fastest aircraft in the world. Number 10 is Sukhoi 27. The Sukhoi 27 is a Soviet-origin twin-engine super-maneuverable fighter aircraft designed by Sukhoi, Russian-made fighter jet which is compared with the US F-15 fighter jet. Sukhoi 27 can reach a top speed of Mach 2.35. Number 9 is F111 Aardvark. The General Dynamics F111 Aardvark is an American supersonic medium-range interdictor tactical attack aircraft that also filled the roles of strategic nuclear bomber, aerial reconnaissance, and electronic warfare aircrafts in its various versions. It can reach a top speed of Mach 2.5. Number 8 is McDonnell Douglas F-15 Eagle. The F-15 has been claimed to be one of the most successful aircraft ever built and is still in service with the US Air Force. The Eagle's twin engine and thrust-to-weight ratio of almost 1:1 can propel the 18,000-kilogram aircraft to more than 2.5 times the speed of sound. Number 7 is Mikoyan MiG-31. Also known as Foxhound, this interceptor aircraft was developed by the Soviet Union and produced during 1975 to 1994. MiG-31 is unique because of the fact that it can fly in supersonic speeds in both high and low altitudes. At high altitudes, it can do 2.83 Mach, and in low, it can do 1.23 Mach. Number 6 is XB-70 Valkyrie. The XB-70 Valkyrie was a unique aircraft with 6 engines which together could accelerate the 240,000-kilogram aircraft to a velocity of Mach 3. This speed resulted in the frame of the aircraft being heated up to as much as 330 degrees Celsius in some areas. Number 5 is Bell X-2 Starbuster. The Bell X-2 Starbuster is a research aircraft purposely made to discover the effects of flying since 1945. A rocket engine was used to power this aircraft, and this aircraft was able to achieve the stunning speed of Mach 3.196, and the aircraft was unstable beyond that. Number 4 is Mikoyan MiG-25. Mikoyan MiG-25 is also known as the Foxbat. It is a unique aircraft that made use of stainless steel design, and this aircraft is an example of Soviet superior aircraft technology. The Foxbat made its first flight in 1964, and few years later, in 1970, it entered the service. The top speed it can do is Mach 3.2. Number 3 is Lockheed YF-12. Lockheed Design's YF-12 is an interceptor designed for the US Air Force, and this aircraft design was based on the top-secret Lockheed A-12 reconnaissance aircraft. Only 3 models were made, and each cost around $15 to $18 million. This particular aircraft can achieve a top speed of Mach 3.35. Number 2 is Lockheed SR-71 Blackbird. The SR-71 Blackbird's main objective is to outrun threats during missions. 32 Blackbirds were used, but unfortunately 12 of them were lost in accidents. None were shot down by the enemies, and it was decommissioned in 1966. The SR-71 can achieve a speed more than Mach 3.3. Number 1 is North American X-15. The North American X-15 was a hypersonic rocket-powered aircraft operated by the United States Air Force and the National Aeronautics and Space Administration as a part of the X-plane series of experimental aircraft. This aircraft has the current world record for the fastest manned aircraft, and its maximum speed was Mach 6.70. So that was the 10 fastest aircrafts in the world in 2019. Don't forget to smash that like button and the subscribe button if you've enjoyed the video, and stay tuned for more videos.
Okay, so just wanted to mention two things about this video. I think it's 2:11 somewhere here.
240,000 kilogram.
Okay, so I think it was the first thing I would like to make a note is about MiG-31, number 7, a Foxhound aircraft.
Number 6 is XB-70 Valkyrie.
I was going to mention something about it. Just a second.
One is unique because of the fact that it can fly in supersonic speeds in both high and low altitudes.
So this is important in terms of our class, for example. She says MiG-31 can fly, what was it, at Mach 3.
At high altitudes, it can do 2.83 Mach.
Mach 2.88. So it's quite high-speed aircraft. And she says that it can fly at supersonic speeds, both at high altitudes and also at low altitudes. Now, that's a big issue because normally, flying high speed is not easy. You need a lot of power, a lot of propulsion power, whereas powerful engines and very optimized aerodynamic design. But generally, flying at high Mach numbers like these at high altitudes is easier because of the at high altitudes we have very low air density, so also the temperature is lower, so speed of sound is lower. We will see the temperature, speed of sound relations and everything, but as the temperature goes down, speed of sound goes down, so you actually need to fly at, let's say, you do not have to fly at extremely high speeds to fly supersonically. But let's say you are at sea level, okay? At sea level, air is very dense. So the density is 1.225 kilograms per cubic meter. So at those very high densities and flying supersonically is very, very tough. So not every aircraft can do that. So, but this was mentioned in the video that MiG-31, the Foxhound, as the Americans call it, it can fly at Mach 2.8. I mean, not the maximum speed, but it can fly supersonically, both at high altitudes and low altitudes. It's a big issue in terms of aircraft design. Another thing that I would like to mention is about the number 6 aircraft, the Valkyrie, I think it was.
And in low, it can.
Let me fast forward a little bit.
Engines which together could accelerate the 240,000 kilogram aircraft to a velocity of Mach 3. This speed resulted in the frame of the aircraft being heated up to as much as 330 degrees Celsius in some areas.
So that's the other thing about compressible high-speed flow. It's a very big aircraft, as you can see. It's 115 tons, okay, 115 tons of metal that is flying at Mach 3. So this is really incredible. Now, the thing is, once you start flying at these high Mach numbers, I mean, high Mach numbers still, it's supersonic, but not hypersonic, it's Mach 3. The thing is, because of these high speeds, when this high speed, very energetic flow, which we will have to do all these calculations in this class, when it actually, is going around your aircraft, in some parts, there will be some stagnation points and everything. The Mach number will be forced to go down to 0, okay, at those stagnation points. So then if you force that very energetic flow to stop, basically, the question is, where will all that energy go? Because energy just cannot disappear. First off, thermodynamics says that. So all that high kinetic energy, I must say, goes to increase in temperature. So generally, one problem of flying very high speeds or at very high Mach numbers is that you end up with very, very high temperatures on your body, on the flight vehicle body. And in the extreme case of space re-entry, meaning that if you have a space vehicle, it could be just a capsule, or it could be like a space shuttle or whatever, is, let's say it's operating in space, and for whatever reason, it wanted to go back to Earth. So it has to go through the upper layers of the atmosphere, and then it's going to start initially in space. There's no air, and it's going to start hitting the air molecules. And the initial re-entry Mach numbers can be in the order of Mach 20 plus. So when you're flying at Mach 20 plus, the temperatures increase enormously, and the vehicle has to survive that. And we need to think about how we need to insulate, good insulation from, or heat shields and everything. And it's a part of this aerodynamics 2 class. So we will learn how to calculate those temperatures, for example. If you know the flight Mach number, if you know your altitude, we will learn how to calculate those high temperatures that the aircraft will be exposed to, okay? So it's a part of this class. It's a part of learning or dealing with high-speed aerodynamics. And I must say, this does not only happen on Earth. A few weeks ago, another rover, the Perseverance rover, actually was landed to Mars. I don't know how many of you follow that, but we had the same problem as aerospace engineers when entering from space to Mars atmosphere. Enormous amount of friction, due to enormous amount of friction and due to compressible flow. It's a different gas though, it's not air, of course, it's mostly carbon dioxide, but entering into that atmosphere creates also a lot of heating. We can calculate with the methods that we're going to learn in this class. And there was a heat shield involved. I don't know if you I watched it live, the landing process, which takes 7 minutes to land the surface of Mars. And there was a heat shield involved to prevent the vehicle, for example, from that aerodynamic heating. The job of an aerospace engineer like you is to calculate the amount of temperatures that a vehicle like that will be exposed to, and also design a heat shield in terms of materials, in terms of heat transfer calculations, to be able to resist that aerodynamic heating. So that's what we're going to learn in this class, okay? And of course, all the vehicles that we have seen, the fastest 10 planes, are all manned. And the last one that we have seen is actually a hypersonic vehicle. So this number one is X-15. It's an experimental vehicle just to test some hypersonic flow physics. It can fly faster than Mach 5. But of course, these are all manned vehicles. Of course, there are unmanned vehicles, meaning that there's a long list of missiles that also fly very, very fast. Most of them supersonic, but also there's some of them are low supersonic, some of them are high supersonic, close to Mach 3, Mach 4. And also in recent times, different countries are developing hypersonic missiles. Of course, those are all for military applications, and high speed flight is mostly military applications for I must say, defense industries. For civil aircraft, we had one example for supersonic flying passenger aircraft, which was the Concorde, which flew long time, almost maybe 40 years, but due to many, many issues, it was decommissioned. And in the world right now, we do not have any commercially flying supersonic passenger aircraft. There are different efforts to design a new one that's going to replace the Concorde, but it's not still commercially available due to different reasons, due to different basically physical reasons in aerodynamics and the cost of doing that. So the next video that we're going to see is related to some of the physics that we're going to learn in this class when you start to fly at high Mach numbers and what's going to happen around your aircraft. So let's watch that. This is just a second. This is also a 5-minute long video. Yes, question?
May I have a question about the
Yes.
other video?
Yes, please.
How do they decide on maximum speed of an aircraft can reach? I mean, usually max speed is relative to airspeed of the aircraft that is in.
Mhm.
I mean,
Yes.
Can we have a lower max speed but higher speed in kilometer hours compared to two planes?
Good question. The thing is, when you start designing an aircraft, you have to decide what we call a design point. A design point means you have to decide on few parameters. Those parameters will be input to your equations, I must say. One of these is the altitude, for example. So you have to select a flight design altitude. You have to select the aircraft that I'm going to design. So let's say its design flight condition will be at 10 kilometers. So I'm just making up numbers right now. 10 kilometers is a typical number for a passenger aircraft. So that's the first thing. So once you select that altitude, this means that from standard atmospheric conditions, which you might have seen it in your previous classes, you know your ambient temperatures, for example, you know your ambient pressure, you know your ambient density, atmospheric density at that altitude. So those will be set by that first choice. Second is one of the next choices that I must say is going to be your Mach number. You have to choose, you have to decide, I'm going to design an aircraft that is going to fly at that altitude and at Mach, for example, 0.8 or Mach 1.2 or Mach 2, okay? So, or it will, if it's a passenger aircraft, it's a little easier to do because passenger aircraft during their cruise, for example, from one place to the other, they basically assume a constant Mach number and a constant altitude flight, and they do that for a long time. For example, let's say a Boeing 777 is flying from Istanbul to New York, let's say, or Tokyo, let's say. It's a long flight for 10 plus hours. Aircraft Mach number and altitude is almost constant in that case. If it's a military aircraft, it's a little bit more difficult story because military aircraft will have more requirements. There could be a design Mach number, which could be subsonic or supersonic, but let's say if it's subsonic, we could still want supersonic flight capability. And when we say supersonic flight capability, what is it going to be? It's going to be 1.2, 1.5, 2, 2.5. So all these will have to be selected, okay? So depending on that, and there are also other supplementary information, design decisions that you need to make. And then based on all that information, you start designing your aircraft. So those will come basically in the coming years in the aircraft design class, you will partly see those.
So Hocam, can I ask something too?
Of course, please.
The sonic condition we mentioned in the first lecture, do we treat it more like a threshold, like a barrier, or can it be maintained for some time?
Generally, we do not have or let me put it this way, we do not design aircraft to have sustained flight at Mach 1, okay? Because Mach 1 is in the transonic regime. The flow physics is quite complex, and when you let's say flying subsonic and started to accelerate and you are starting to reach towards Mach 1, there will be a great amount of increase in your drag. We will see all of these. That's the part of this class, the dealing with that drag increase, how to actually surpass Mach equal to 1 and go to supersonic speeds. At around Mach 1, the drag increases to enormous amounts. When you can somehow pass Mach 1, drag actually drops down, okay? So generally, we do not design aircraft to have constant Mach 1 flight at sonic condition or have, let's say, sustained flight at around Mach 1. Either we design aircraft that fly maximum around 0.88283, or we design aircraft that fly faster than Mach 1.2. So generally in the transonic regime, we do not design aircraft to have sustained flight. We will see why that's related to flow physics and that's related to compressible aerodynamics. We will see why in this class. Let's watch this video and maybe I will have a few more comments related to that. So it's 5 minutes. Let's start.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shockwave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
So as you can see, let me try to find that. This guy is actually you guys. It represents you, the scientist who is trying to determine the pressure field by solving Navier-Stokes equations. That's aerodynamics 342. This is you guys. So there's actually one more video that is shorter. This is related to sonic booms. Let me try to quickly open it.
Hocam,
Evet.
what was that Z shape in the video? I didn't get it.
That's the shape. That's the, you hear double booms because of the aircraft shape. That's indicating that double boom. Let me open up this video first. Oh, it's actually already open. Okay. So share. Okay, this is 3 minutes, so let's quickly see this because this is complementary to what we've seen regarding sonic booms and Mach cone and everything. By the way, we will learn all about what we saw. For example, first of all, we will learn what is speed of sound, what are sound waves, and how is this Mach cone created, and how are the shock waves created, and how do the shock waves actually change pressure, temperature, density, velocity, Mach number on a flying vehicle. We will see all equations related to that, and we will, the entire compressible flow class will be related to the life of that guy that you've seen in the video, or girl, trying to calculate the pressures, temperature variations, Mach number changes when a shock wave or a Mach cone passes, or the flow passes through one of these. So now what we're going to see is more related to aircraft.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shockwaves. Shockwaves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots.
So, okay, just one thing that I would like to mention regarding this video, and that's also going to be a part of this class, is this, okay? So when an aircraft is flying, there are shock waves formed around the aircraft, and it's related to the Mach cone that you have seen.
Supersonic,
And,
transonic, or even near.
especially as you start flying faster and faster, you would like to have your wings swept back, as you see in this
Supersonic flight.
this video. So it's going to stay in the Mach cone, but there are other physical reasons that we sweep back the aircraft wings for high-speed flight. This was when aerospace engineers were trying to design supersonic flying aircraft after World War II. They did not know this. I mean, they were flying initially, for example, with X-1, which is this aircraft. It had straight wings, it's not swept back, and it was having very much difficulty going past Mach 1. It had an extremely powerful rocket motor. Even it had that powerful motor, it was having very much difficulty. So in any case, they were able to they were able to increase the power of the rocket so that it passed Mach 1. But in later years, they realized that actually you do not need that much power. All you need to do is to change in the aerodynamic shape of the body. One of the changes is related to the wings, and it's giving the wings a sweep back, sweep angle, so that it reduces the drag that aerodynamic drag that it encounters at those high speeds. There were other geometrical modifications to the aircraft shape. We will see all of those also in this class. Okay. Good. So as you might have noticed, this a shock wave that is created by a fast-flying aircraft is a very violent phenomenon, okay? And when this shock wave comes and passes over you really
It's 661 knots on an average day at sea level. And sometimes to that speed through waves,
let's hear
speed
that.
increase that happens.
Let's hear that one more time.
760 miles per hour, or 300.
Anyway, I will put the link in the chat box right now, but this shock wave, something is happening across the shock wave. And that's what's happening is the flow properties. Let's say you are inside the aircraft, you're flying the aircraft, so the flow is passing around you. The flow suddenly encounters this shock wave, and its properties almost instantaneously change. Its pressure suddenly increases, temperature suddenly increases, and when that shock wave comes and hits you, if you're standing on the ground, passes over you, that sudden, almost instantaneous increase in pressure, basically we hear like a big explosion, explosive sound. So that's why we call it sonic boom. Okay, so we will see in this class how to deal with shock waves. There we will categorize shock waves, different types of shock waves we will deal with, and we will learn equations in terms of how to calculate that instantaneous jump in flow parameters like pressures, temperatures, density, Mach number, velocity, and everything. Okay, so let me quickly copy these links to the chat box, and I will say a few more words. Where is my chat box? Okay, this is one. And and this is another one. And we have seen 3 videos, right? And which one did we see? Okay, this is the first one that we have seen. So the links are on the chat box. Regarding Ufuk's question, so I got you so excited that now you want to know how many students will be in the lab groups. Very good. I don't know, probably, yeah, 4 students maybe. We will see, okay? Depending on exactly how many students will be taking this class. Okay, so we will learn everything, all the flow of physics. And since this is not a concepts class only. This is an aerodynamics class. So as you might remember from aerodynamics 1 class, we learn flow physics and we learn mathematical tools in terms of how to deal with this flow physics. And the first thing that we're going to learn, of course, we are living on Earth. So the first thing that we're going to learn is that we are basically designing vehicles that will fly in Earth's atmosphere. So in air, in the gas that we call air. Air is, of course, composed of basically nitrogen and oxygen, and mostly, let's say. And how do we deal with vehicles that are flying at high speeds in air? So the first thing that we're going to learn is the concept of what we call a perfect gas. So let's go back here. I'm just going to introduce this, then we're going to stop for today. But the first thing that we're going to learn is the definition of what we call a perfect gas. This is very fundamental in high-speed aerodynamics to understand this, also in, of course, thermodynamics as well. Just a quick word, when we say gas, this, to keep things general, we say gas, but this is, of course, as applied to air if you're dealing with Earth's atmosphere. Now, the thing is, we know that any gas is actually composed of molecules, right? So we say we are talking about air. Air is nitrogen and mostly nitrogen and oxygen. There are also other small amount of other gases, but mostly nitrogen and oxygen. And there are molecules, and these molecules are composed of atoms, and atoms are composed of electrons and everything. So the thing is, and these are in a gas, all the molecules, let's say, whether these are oxygen or nitrogen molecules in air, O2 or N2, they basically are in random motion, right? So they are randomly moving around, sometimes hitting each other, or sometimes hitting solid surfaces. Solid surfaces could have could be composed of other molecules. So they are randomly moving and randomly interacting with each other. So there's also what causes this random motion is that there are what we call intermolecular forces that basically determine this random motion. Intermolecular forces are caused by many, let's say, many different reasons, and causing the actual motion of these molecules. Now, when we define a perfect gas, that's basically, let me check it from here. That's basically, let's say, these gas molecules that are present in air, or we could be talking about, for example, the gas of a jet engine. This is also the same. This is also similar. It's a gas, the exhaust jet of a exhaust coming out of a jet engine is not air anymore, right? We have other carbon dioxide, water vapor, carbon monoxide. When these molecules are sufficiently far away from each other, we can there could be a gas state. We can ignore the effects of intermolecular forces. Okay, so when this is the case, so when it's the case, when we have a gas, let's say, in which we can neglect the effect of intermolecular forces, we define this one as a perfect gas. So let's say this is a gas in which intermolecular forces can be neglected. Okay, this is how we define a perfect gas, or sometimes, of course, we call it also an ideal gas. So you might have heard these terms, maybe, if I'm not mistaken, in thermodynamics class. Okay, a perfect gas or an ideal gas. So this is generally true for most of the gases that we deal with in Earth's atmosphere, and it's definitely true. And the true meaning, it's a reasonable approximation to reality that considering air to be a perfect gas. Now, the nice thing about this perfect gas approximation is that when a gas can be considered as a perfect gas, we can use what we call the ideal gas relation. So we can relate the pressure of that gas, which is a macro scale property. It's not a molecular property. Pressure is a macro scale property, global property. We can relate the pressure of this gas to the density of the gas and to the temperature of the gas, and all of these three parameters are macro scale quantities. They are not molecular quantities, and we can relate pressure to density to temperature through a constant R. Here, let me write this down and we will stop for today. This is P is pressure, rho is density, T is temperature, and R is what we know as the gas constant. So for every type of gas, this R has a different value. This is known as the gas constant. For air, air is a certain type of gas. This is equal to 287 joules per kilogram Kelvin, okay, for air at standard conditions, for air at standard conditions. Now, if you're dealing with another gas, let's say another perfect gas, not air, but let's say Martian atmosphere, R will be different. Okay, what is the R for Martian atmosphere? You can look it up from the web, it's already known. But if you're dealing with, let's say, combustion gases after the combustion chamber of a jet engine, it's not air anymore, it's a combination of other molecules, R will be a different value. But for, let's say, designing air vehicles, designing vehicles that are going to move in air, an air is approximated quite reasonably as a perfect gas. So this ideal gas relation, okay, P is equal to rho RT, or this is also known as the equation of state of a gas, actually, equation of state, can be used to relate pressure to density to temperature with a properly chosen R value for that specific gas. And let me write these. All of these are, as I've said, macro scale properties. They are not molecular properties. Macro scale properties. What do I mean by that? Pressure is an indication of all these molecular motion, that is random motion that is happening. Temperature is another indicator of that, all that random molecular motion that is happening, and density is related to that. But these are macro scale properties. We do not talk about, for example, the pressure of a single molecule, no, or the temperature of a single molecule. No, we talk about pressure of the fluid, a collection of molecules. For example, pressure of a fluid particle, as we define in fluid mechanics, temperature of a fluid particle, or temperature of the gas at that point, pressure of the gas at a certain point. So these are macro scale properties. So tomorrow we will pick up from this point and continuing our discussion on our first fundamental definition of gas conditions. And we will relate them to inviscid compressible aerodynamics quite soon. Okay, so let me stop recording. Stop recording.